last time what our long-term goal in the project is?
The robot?
Yeah. Remember that? I have this arena set up with a robot that kind of wanders around and tries to hit a target. On there. And the way we were going to get to this point was we would generate a random expression, have the robot evaluate that expression every time it takes a step, and that expression tells us how it's going to turn. So it's going to take a step, evaluate the expression by plugging in for x, how many steps it has taken. It comes out with a number, and then it turns that amount. And then it takes a step, and then does this thing again. So it should produce kind of some kind of walk around the arena. So essentially, this is a visualization of the function, except that x is not an axis. X is how far along this path we are. So our x is increasing as we take a step. And that's what allows this path to follow something that doesn't quite look like a real function. You know, in what's it, algebra, you learn what a function is. And a function is, it needs to be something, but it never doubles back on itself. Or it never has two or more stacked up. Remember that definition of the function? So, but this is a function where x is not a straight line, it's going across a curve, and so the curve actually can double back on itself. Okay, so just to kind of alleviate that concern that, hey, this is supposed to be a function, but it appears to be coming back, and that's because the axis is actually twisted up. Is that okay? Mm-hmm. So once we have this robot wander around, we're going to figure out, and we're going to do it, we're going to generate, let's say, 100 random expressions, have 100 robots all wandering around, and then we'll figure out which one came closest to the target. And then use that one, or maybe there'll be a couple that came closest, maybe we'll use 2 or 3, use those as the basis for the next generation of robots. So we'll take this expression that we came up with and go, this one came close, all we need to do maybe is just tweak it a little bit to come up with something that gets a little bit closer. Some of you are taking biology. Took it in high school, right? Yeah. So this basically represents the DNA for that robot. This is the programming for that robot. So if we have an organism that works pretty well, but we just want to kind of evolve it, what do we do to its DNA?
Change it a little.
Change it a little. So we can do something like mutate. What does mutate do to that DNA?
Takes one of those things and randomizes it.
So which thing would you randomize here?
Just one of them at random.
One of what?
The end values.
Something down here. So we could take this 3 and make it just change it to something else. What about changing something here?
Maybe.
Maybe? Why is that problematic?
We fundamentally change the function.
Yeah. So if we swap this with like a plus, then it's still a valid tree. But if we swap it with a log, that's not valid anymore. What do we do with one of these branches?
You just have to get rid of it.
And then which one do you pick? Randomly. So I think that swapping out one operator for another operator presents kind of more of a problem than maybe it's worth. That mutate is an operation more along the leaves here, of just taking one of the values here and just randomizing it, or changing it by adding 1 or subtracting 1.
What if you did log of 10x?
Then that would be like, that only applies to log.
Yeah.
But if we swap it out for sine,
You could do sine 10x. You could still do that.
Now, if you do log, then what you have to do is, have to go log, and then put below it a times, and then, so you're basically changing the structure of the tree rather than just twiddling a little thing in here. So I think that for our purposes of doing mutate, just changing the leaves is probably sufficient. Okay? And so what do you think by replace?
Replace an entire chunk of the tree with something else.
Yeah. So take this whole piece and replace it with a randomly generated tree. take this and identify some portion of this one here and replace them with each other. So essentially, these two robots are sex, and they swap their DNA. So we get some attributes of this robot end up in this one, and some attributes of this robot, actually, it's not that we swap them, these two, is we do the swap in their offspring.
So you just sort of mix it up and have a whole other thing.
Yeah. So we get two robots, we have them generate an offspring, and then we kind of just start swapping pieces of them around. So we could replace one subtree of one robot with the subtree of another robot, or with a subtree of a randomly generated thing. Or even take these two and swap them. So what we're doing with replace here is identify a random subtree and then replace it with another tree, or expression in this case. And that replacement could come from some other robot. It could just be randomly generated. It could be some other spot in the same one. Just that you're finding one spot in this tree, replacing it with a different one.
This is much more like microbiology than full-scale biology. Sort of like viruses. Viruses will randomly exchange DNA.
Right. And hopefully come up with something that's, well, better for the virus, worse for the host.
Yeah.
Make it more likely to survive.
Which is why people are afraid that if pigs get bird flu, suddenly we'll be able to get the
Oh, I
bird
just
flu.
heard today that, in fact, they've got some suspicion that the bird flu is actually going human to human now. So it's mutated from a couple of years ago, where it was going among the chickens and the birds, but that was it. It wasn't getting to the humans, but now it's going human to human.
Yeah.
Which is scary for us because we're totally unprotected against that.
Well, we were able to get it from birds, which was extremely rare. But then pigs started getting it, and pigs share the same sorts of viruses that we do. So as a result, it's now able to jump from person to person.
So those bird avian flu viruses have mutated themselves and started swapping DNA around to come up with something that works better for it, more likely for it to survive. You also see it nowadays in elephants in Africa are being born without tusks. Why?
Because
Because they don't get killed for their. So they have no tusks to get poached for, and so they're more likely to survive. And then I also heard that there are some villages in China where people are being born now without wisdom teeth.
That's not just in China though, that's happening like slowly worldwide. You don't need them anymore.
Yeah, as it kind of spreads around. The idea there is that without wisdom teeth, you naturally have dimples right there, which makes you a little bit cuter. And therefore more likely to have offspring, who are also born without wisdom teeth. So that's just kind of interesting to see this sort of evolution happening right in front of us, but on a relatively shorter time span. Okay.
here in America, that's not likely to happen because we just yank them at a certain age anyway.
Yeah.
Just get them yanked.
So yeah, so we're all cute because we don't have wisdom teeth. Although there's that week after you get them yanked where you're not very appealing at all. Okay, so to be able to do something like a swap, or a replace, or a mutate, the first thing we need to do is be able to take an existing expression and clone it. Make an exact duplicate of it, and then start tweaking the duplicate. And when I say tweak, you know, I don't mean taking heroin, right?
All drugs.
So we need a new behavior for expressions called clone. We need to be able to take an existing expression and make an exact duplicate of it. Because we may be able to take an expression actually and make 100 duplicates of it, and then start messing around with those. Okay, so let's talk about how do you clone something. Go back to our list. What kind of thing is this? 5. It's a kind of 5. It's a compound. This is a compound. This is a compound.
Singleton.
This is a singleton. And I have a variable called A that points to this list. And now I want to be able to go list B equals A dot clone. And A will return a copy of itself.
It's kind of unnecessary, just equal A.
But if I go B equals A, then D will point to the same thing that A points to. What I want is for B to point to a whole separate copy with the exact same numbers. But then if I mutate this 8, it doesn't affect A. I could wrap this up in a loop and go A dot clone, 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 and I get dozens of copies of A. So let's talk about how do we make a list clone itself? What do you think should happen?
Just walk down the list and read it and write it to another list.
So we're going to ask number 5 here. Remember, that's what A is pointing to. A is actually pointing to number 5. It's not pointing to the whole list. It's pointing only to number 5. So we're going to ask number 5, clone yourself. And then, because this is also a list, and this is also a list, and this is also a list, all of these need to know how to clone themselves. So if you're the number 5, how would you clone yourself? Make a new compound.
Set the value of that one.
Set the value of that one.
Should the one of
So I would go new compound. And then I need 2 things.
this.
Your value and
I put my own value here.
your class.
Does it make sense? I take my own value and copy it into this new compound. And then what do I put here?
The one is one copy right next.
The list that you point to.
Right, the list that I point to. So if I put next here, what will I end up with?
Compound 5 pointing to another compound. Maybe with an 8 in it.
So will the picture end up looking like this? So number
Well,
5.
as long as it keeps repeating,
number
yeah.
5 here.
Yeah, if you can get that to repeat.
Spawned off a copy of itself, right?
Yeah.
And then what does next point to?
Compound with 8.
Points to this one.
And then that one copies itself and points to the next one, and then that one copies itself.
But what we wrote here, is this compound here. The next just points to the next one.
Okay, so then
So-
you have
so I
a
don't
copy
get-
of 5 pointing to the old 8.
Yeah. So I get a new 5, but it points
Pointing
to
to
the
the
old
same
8.
8, yeah.
And that's not a complete copy.
Got it.
Next dot value.
No? Either way.
Next dot clone.
Next dot clone. So the next thing that the new compound points to is a clone of the next thing. point to a clone of the 8. And then who's the 8 going to point to?
Clone of the 1.
A clone of the 1. And the 1 will point to a clone of the 2, and the 2
Point to null.
is a singleton,
Yeah.
so it never points to anything else. Okay, so clone is just going to return a new compound with a copy of its value and a clone of the next thing.
So you're going to have to put something there so it doesn't just walk off the list, right?
Well, singleton, so this is the clone for compound.
Yeah.
Then there's another clone for singleton. So this is inside compound. This is inside singleton. A singleton returns a new what? A new singleton. And what does it put in for its one argument?
This stuff.
Its own value. But because there's never any next for this, the singleton just produces a clone of itself, and there's nothing else to do. So this is what stops the whole thing from just walking off the end. Okay, the last piece is, what does clone return? A list. Should we try it out? Yes, please. Turn off some lights. Actually, since the windows are open, I'll turn off all the lights. Now. Okay, so every type of list, singleton, compound, knows how to clone itself. So where do we start by, where do we start implementing this method?
Interface.
Yep. So every list knows how to clone itself. So we'll go public, list, clone. And then we'll go to compound, public, list, clone, return new compound, this dot value, comma, I can just say value, comma, next dot clone. Singleton, public, list, clone, return new singleton, value. And what do I do for empty?
Nothing.
Return new empty.
Public, list, clone. You said nothing, and then someone else said
Return empty doesn't matter.
return new empty.
It'll never get called.
Well, for a general list, it might. So I create an empty list and I want to clone it.
Yeah, but not in our thing over there.
Okay, so list A equals new compound. Actually, I can do it this way. Does that work?
Yeah.
So what type of thing is A going to be?
A list.
A what kind of list? It'd be a compound. So even though I initially made it an empty, when empty did its add, replaced itself with a singleton, and then when that did an add, replaced itself with a compound. And when I go through the whole chain, I end up with A actually pointing to a compound. And so A dot toString needs to be 1, 2. Which is this exactly backwards, remember, because it's always adding to the front. Side, that works. All right, now I should be able to go list B equals A dot clone. Now, how can I prove that this is in fact a clone and not just
Remove one from A, but not B.
remove one from A? So A dot remove,
To string.
A dot to string,
And then check B again.
A dot to string, oh, yeah.
Something didn't work right.
You know what happened?
Is that not
Is
static?
when we do A dot remove, it returns
Oh.
the new list to us. We should have gone A equals A dot remove. Does that prove it?
Mm-hmm.
Just for fun, do B equals A.
B equals A.
Yeah. And then to string B and see if it points to the same thing. Okay, cool. Thanks.
So now, let's do mutate on this list. What should mutate on a list do?
Change the first thing, or the most recently added thing.
Pick a
Well, that wouldn't really be mutate, because then you always know what's getting changed. You don't know what's getting changed to, but you always know what's getting changed. Whereas mutate on an expression should be, once I clone it and I say mutate, somewhere in there something changed. But I don't know what, unless I look really closely.
Pick a random component of the list and randomize it.
Okay? Pick a random,
Value. Because you don't want to change the operators.
well, so we'll do it on the list here, and then we'll talk about expressions here. So if we want to mutate this list, we need to identify a random node in there, and then flip its value.
Size 1 to 4, 0 to 3. Pick one and change it.
See, but we don't, so how do we change it? Because the only thing our lists know how to do is add, remove, size, clone, toString. There's nothing here about changing it. Okay?
So I didn't hear, did you say flip its value? Identify a node and do what?
Modify it. Just randomly pick a new value to go in there. And mutate is going to be something that a list knows how to do. So if we add public void mutate to this, that means compounds and singletons and empties need to know how to mutate. Hmm?
We misspelled that, mutate.
So let me mutate that. Like that. So how would an empty mutate itself?
Dude, just remain an empty.
Do you want it to be able to become a singleton?
No.
No? Okay.
So we were talking about that. We don't want to change the overall
Okay.
structure there. So So if we have a list of 4 items in there, we don't want to make it a longer or shorter list, we just want to change some of the values. So an empty,
Can't be.
It'll just be an
itself.
empty, yeah.
It just stays the same. How about a singleton mutate?
Just random number.
Pick a random number?
Yeah.
So let's see, value equals math dot random, and we were going, oh,
10 to negative 10.
negative 10 to 10, so then we're going to multiply by 20, and then subtract 10. And a compound.
Same thing.
Same thing? So the way we wrote it here is rather than identifying a specific node to mutate, every single node mutates itself.
To cast the whole thing as an end.
Oh wait, value, oh, value is an int. Yeah, okay. What happened here? Singleton is not actually, does not override and did I misspell mu? Mutuate, yeah, I did it again. There we go. Okay, so let's make a list, and then we'll go a.mutate.
A equals A dot mutate.
A equals a.mutate. And mutate doesn't return anything. Oh,
There you go. This would be different.
Do we want it to mutate the whole list every time, or
Yeah, how
do we
come
also do it?
yeah, how come it didn't work the first time?
what's happening?
It's only just less than.
Yeah, it's not,
It's only changing the first item. It's not changing any of the others. Why is that happening?
Doesn't get passed through.
Yeah.
So when we go a.mutate, who are we sending that? Who? Which compound?
just the front.
Just the front one.
Yeah.
So the front one changes its value out,
That's bad.
and then that's it. So how can we get it so that the whole list mutates?
So
We
next
just do
dot
Gemini.
mutate.
Then go with next.mutate. To pass down that message to the next one and say mutate yourself. Do we have to do this to any of the others?
No.
No? Okay.
Because you want it to
But
stop.
singletons will never have anything following it. Better? Okay, you like that?
Mm-hmm.
Any problems with it? from a biological standpoint, any problems with it?
Changes them all.
It changes them all.
Yeah.
Remember, so mutate on a biological thing is just a little bit of it gets changed. And how much of that gets changed? That's random. So maybe some things change. Maybe we actually do mutate and nothing changes. So what does that suggest we have to do?
Something to determine how much to change. Maybe.
If we look at compound here, we could wrap this up and say, there's an X% chance that will actually change the value. Right? So basically we're gonna roll the dice, and maybe it's a 100-sided die, and we can say there's a 1% chance of actually change this value. There's a 99% chance that nothing will happen. But then it'll tell the next one down the line, go ahead and mutate, and that'll do the same thing. It'll roll the dice. So every single node has a 1% chance of changing its value. So how do we do that?
Throw another switch in there.
So we need to say if math.random is going to produce a number between 0 and 1. And if we want to give something, well, in order to know if this is working, we should probably be more than a 1% chance. Maybe we'll do a 50% chance. So there's a 50% chance it'll mutate. So if this number is less than 0.5, do this thing. Right? So we're going to roll the dice. If we get a number that's less than 0.5, we'll mutate the value. Regardless, we'll tell the next one to mutate. Do we have to do this to any others?
No.
Yes.
Singleton should probably also do that. There's a 50% chance that a singleton will mutate. Anything change?
Nope.
Ina, you got your hand up?
No.
Yep.
Two of them changed. So either two of them changed, or all of them changed, but two of them happened to pick the same value. Like that better?
Yeah.
So I've got this set to a 50% chance. What would I do so that there's a 10% chance that it will mutate? Do I make this 0.1 or 0.9? 0.1? Is it working?
Yes. It's trying to.
That's how.
There you go. There. So I had to do that, 5 times, but each one of these is 4, so essentially there were 20 mutates called in there, and one of them triggered, so that's
5%.
5%.
Yeah, but, if we do this more, I think, it's definitely not 90%. It's definitely not changing most of the time. So I think it might be useful so that instead of it always just mutating by a fixed percentage, that we can somehow modify that percentage very easily. So rather than having to compile the whole program again, we can just pass in what the percentage is. So we can change the interface so that mutate takes a double percent. I'll call it chance. It's not really percent, because percent would be technically 0 to 100. And empty chance, but it doesn't do anything with it. Oh, mutate. Pass that along. There we go. And actually, this now gives us the ability not only to be able to set the amount of mutation at the time we call it, but also actually to change that amount as the simulation is progressing. So maybe early on in the simulation, there's a great chance of mutation, but later on, there's a less and less chance of mutation because we're kind of, our robots are getting better and better and better, so we actually want to change them less and less and less as time goes on. All right, so that's mutate.
We're gonna need a way of measuring the distance from the robot to the point, right?
Yeah.
To see how close we are.
Yeah. In fact, I'm thinking about just basically giving you this. I'll show you how it works.
Okay.
But what I've got here is it walks the path and it records the locations along that path. And then after the path is done, it runs through, it stores them all in an array.